Okay, we talked about in the last notes about the reactions between strong acids and strong bases. Now what we're going to do is we're going to look at some calculations involved in the reaction, those neutralization reactions between acids and bases. The idea here would be, what if you started, let's say example, you started out with 30 milliliters of 0.1 molar acetic acid, and you added a certain amount of NaOH. Is there a way to calculate the pH of the resulting solution? Maybe you haven't neutralized all of the acetic acid with the amount of NaOH you did. Maybe it's at the equivalence point. Maybe you've had the acetic acid and you've added enough NaOH that all of the acetic acid has been neutralized and you have excess hydroxide. So if you kind of think what we're thinking about here is there a way, if you think about how this relates to acid-base titrations and titration curves, is there a way to calculate what the concentrations of the species in the reaction between acid and base, what those concentrations would be if you add a certain volume and molarity of acid to a certain volume and molarity of base? Like with titrations, there's going to be different scenarios. And we are going to look at the scenarios. The scenarios that really, the two main scenarios will be if you react a strong acid with a strong base, or you can react a weak acid with a strong base, or a weak base with a strong acid. Now these two are going to solve similarly. But this strong versus strong will be different. Why? Because again, those two guys will react. Their neutralization point will be at pH 7. And one of the things that you know is strong acids and strong base do not have an equilibrium. Okay? And so when you are presented with a problem that involves an acid-base reaction, you always have to ask yourself three questions. Okay? And these are the three questions. One, when you mix the two solutions together, let's say you mix two solutions together, is there a dilution? In other words, if you add 30 milliliters of an acid to 30 milliliters of base, well, now the final volume of those two is 60 milliliters. So the number of moles that were in there initially will now be in, let's say, twice the volume or in a greater volume. So you always have to ask yourself, in the scenario, is there a dilution? And if there is, what you're going to do is you're going to calculate the concentrations after the dilution has occurred, after the two solutions are added and the dilution has occurred. The next thing you're going to ask is there stoichiometry? In other words, are you going to, is there stoichiometry? Is one of the two reactants in excess? Is there a limiting reactant and one's in excess? Are they in the stoichiometric amount and you're at the equivalence point? You're always going to look at, I think most cases, you are going to have the answer to is there stoichiometry is yes, because you're going to add a certain amount of an acid, like a molarity times a volume of an acid to the molarity basically times the volume of the base. Okay, and so when in this application or in this idea of is there stoichiometry, what we're going to look at is sort of a new kind of table that's like an ice table, but it's called a before, change, after table. And it's going to be key to doing the stoichiometry in this acid-base reaction. Okay, and in a way, the before, change, and after are going to kind of get at where are you? Is stoichiometrically more base than acid, more acid than base? Are they stoichiometrically equal, etc., etc.? And so that'll be the key. So the before, change, after table. Then finally, once you get to the get the stoichiometry done and you find out what you have present and what concentrations you have present after the two things react stoichiometrically, if a weak or strong or weak or weak acid or weak base are present, often you have an equilibrium. Not every time, and we will see a case in today's notes where you don't have an equilibrium, but most often when a weak acid or base is involved in a calculation like this, the answer to is there an equilibrium will be yes. And if there is an equilibrium and you want to find concentrations, then you will need to do an ice table. Okay, so this one is probably, not to scare you away, but this is probably some of the most involved, I won't say complicated, but the most involved kind of calculation that we've done this year. Because you're going to have to do, in a way, sometimes 3 separate calculations. One, if there is a dilution, another for the stoichiometry, and if there happens to be an equilibrium after the stoichiometry occurs, after the reaction occurs, if there's a weak acid or base, you're going to have to, most cases, do an ice table. Again, we're going to go through several examples here, the first being strong versus strong, which should be one that you're pretty familiar with and will not involve the third question, is there an equilibrium? And so we'll look at how we deal with the first and the second questions about the dilution, and we'll learn about this before, change, after table. All right, let's start this first scenario, strong versus strong. Now remember, for the net equation for a strong versus strong, it ends up being H plus OH minus gives you water. Okay, or H3O plus OH minus gives you 2H2O. So here's the scenario. It says, what will be the pH of a mixture of 35 milliliters of 0.200 molar HBr mixed with 25 milliliters of 0.250 molar KOH? This is the chemical reaction written, and again, you can see that the spectators would be bromide ion, potassium ion. It's going to make KBr. Again, this will be neutral, the salt would be neutral, makes water. So you end up with that net ionic equation. Now, let's look at that first question. Is there a dilution? Well, you know me, guys. A picture paints 1,000 words for me. And I always think about drawing a picture. So let's draw a picture of this scenario right here. And, well, I had some HBr. I had 35 milliliters, right, of 0.200 molar HBr. And to it, I added 25 milliliters of KOH, right? Well, the resulting final volume will be 60 milliliters. And so the number of moles of HBr that were in there are now going to be dissolved in 60 milliliters rather than 35, and the OH that was in there, right, the KOH, is now dissolved in 60 milliliters when it was previously dissolved in 25. So the question is there a dilution? Yes. So you need to calculate the new concentration. So you take, remember, so there's, whenever you do a dilution, you use that equation, molarity 1, volume 1 equals molarity 2, volume 2. And then so for KOH, the molarity, the concentration of KOH, right, in the dilution, that would be basically molarity 2, right? It's going to be molarity 1, that's the molarity of the KOH, times the original volume of the KOH, and then divided by volume 2, okay? And you end up with, in this case, 0.104 molar. How about for the HBr? Well, you want to find the molarity 2. In other words, what is the molarity after dilution? So you take the molarity of the HBr times the initial volume, that should be a V, of the HBr, and divide that by volume 2. And then you end up with 0.117 molar. That should not be too foreign to you, but again, it's actually kind of good too, because we learned about solution chemistry a long time ago, and it's nice to have this application brought back up for us since we haven't probably done this for a while. All right, now we'll look at the second question. Is there stoichiometry? Of course there is, right? So you're going to look at the concentration, and here's your reaction. And we're going to set up what we call a before change after table. So BCHA. I called it a BCA before, but sometimes it's like a betcha table. I think that's kind of the mnemonic. That's why they say CH for change. So it's a betcha. Anyway, so what you're going to do here is you're going to write down the concentrations. And then they're going to make the water, right? Well, water's a liquid, so we put I know this is the concentration of my hydrogen ion because that's going to be this concentration over here, and this will be the concentration of hydroxide ion. So before the reaction occurs, right? You're going to mix them together, and just before the reaction occurs, this is what you have. Well, looking at this, these guys are reacting in a 1-to-1 ratio based on the balanced equation here, okay? And so you can kind of see that the OH minus here is going to be the limiting reactant because this 0.104 molar OH minus is only going to need to react with 0.104 molar of H plus, and then it's going to be used up, okay? And so then you have to kind of look at what what's going to be the change, right? And so you know that this, when this reacts, that the OH minus concentration is, what's the change going to be? Well, it's going to go down, and it's going to go down to 0, okay, after. And then for some reason there was a dot here in the previous slide, so I stopped the video and erased it. That should be minus. So then what's the change? Well, this 0.117 molar is going to go down by 0.140, and the kind of times the 1-to-1 mole ratio that it's reacting. So that's sometimes how you see this written. And so that's going to be the change. This 0.117 molar is going to go down by 0.104 molar. And afterwards, you're going to have 0.013 molar H plus left over. So that is going to be the concentration of what's left. There is no hydroxide left. There's 0.013 molar H plus. And so the pH of this solution, this is really the hydronium, then hydrogen ion, the hydronium ion concentration. So to find the pH, take the negative log of what happens after the stoichiometry. There is no equilibrium here because, again, this is strong versus strong. So this concentration of H plus is what's present when the reaction is done. And so, in other words, when you don't react enough OH minus with a certain amount of H plus, you expect to get an acidic solution, right, as a result. So this would be a case in a strong versus strong titration where you haven't added the hydroxide to the equivalence point. Because you had added it to the equivalence point, you would have added 0.117 molar OH minus, correct? Right? See how this kind of fits? Okay. So you are at a point here before the equivalence point in the reaction between an acid and a base. Okay. Anyway, because you have resulting leftover hydrogen ion, the pH is going to be in the acidic range, and to find the pH, you simply take the negative log of that concentration of hydronium, and you get 1.89. Okay, so let's now go through the second of the 4 scenarios that this lecture notes will cover. This would be if you have a weak acid versus a strong base. And so the question might say, what will be the resulting pH, in a sense, if you mix 35 milliliters of 0.20 molar HClO, that's hypochloric acid, with 25 milliliters of 0.2500 molar KOH. Now, in these types of problems, if you have a weak acid or a weak base present, you will generally be given the Ka. And again, you're going to look at this and you say, okay, well, in this scenario, let's start with our questions. Number 1, is there a dilution? Well, it says you're adding these 2 solutions together, so yes, there'll be a dilution. Well, you're reacting these 2 things together, and so there will be some stoichiometry. And then the third question, is there an equilibrium? Well, you really won't know that until you get done with the stoichiometry question, but you gotta think you might be doing an ice table, because whenever there's a weak acid involved or a weak base, a lot of times these guys end up after the stoichiometry with an equilibrium being set up between like a conjugate acid or conjugate base and water. All right, well, let's quickly look at the dilution question. That of course, this is the same as we did before. You want to find the molarity of this solution, right? And you want of each solution after dilution. So this is the molarity 2. So you take your molarity 1 times your volume 1 over volume 2. The same for the KOH, and these are your two molarities at the point where the reaction happens. All right, well, then you need to write your balanced equation. This is kind of why in that when we first started this, 8.1 to 8.3, we talked about writing these equations. So if HClO reacts with KOH, this is a neutralization reaction, you're going to make water, and then you're going to get a salt, right? But in this case, remember, ClO, this sum of HClO stays together, and then you make ClO minus. And so in this case, potassium ion will be the spectator. So this ends up being your net ionic equation, right? Okay, so you're going to do, what's the before change after? The betcha table. Well, before, we just figured out our new molarities. The molarity here and this molarity here, we put them in there. And there's no product because you just haven't had the reaction yet. Well, how is it going to change? Well, looking at this, HClO and OH minus are going to react in a 1-to-1 concentration. And so this guy is going to go down, right? And it looks like that's going to be the limiting reactant because you have more acid molarity-wise than you do base to start, right? They're going to react in a 1-to-1 ratio. And so how's it going to change? Well, this guy is going to go down until it's all used up. So you end up with no OH minus left at the after reaction. And then you end up with the HClO concentration, right? This is going to be neutralized. This 0.1167 molar is going to be neutralized until the KOH runs out. So you end up with, so that concentration minus the concentration of KOH that gets used up in a 1-to-1 ratio. That's what the 1-to-1 there means. So you end up with 0.0125 molar HClO. And then, well, what about the ClO minus? Well, its concentration is going to go up because for every HClO that is neutralized by KOH, you create some ClO minus. Okay, gentlemen, here's where I think these types of problems, I won't say they're the trickiest or most complicated, whatever. This is the challenge of these types of problems. Once you get to the stoichiometry step and it's done, and you figured out that you have, looks like after, well, you still have some weak acid left over. And it is in an equilibrium, right, with its conjugate base. It may not look like it up here, but it does. It sets up an equilibrium, okay? Because, with its conjugate, okay? And so what you write is, well, this HClO is dissolved in water, right? And so it is going to then act like, an acid, right? And so because there's no more KOH left, and so you still have some HClO dissolved in water, okay? But you also have some ClO minus. And so you write the reaction. It's HClO, that's your acid, plus water that it's, in a way the water it's dissolved in, or I guess even the water that it created, will give you ClO minus and H3O. And this will be in equilibrium because the acid and the conjugate base are both present in an aqueous solution, and they will set up an equilibrium. Okay, so to do this, you have to look at what you have. Well, you start out with this HClO 0.0125 molar and ClO minus 0.1042 molar. you assume, remember the hydronium is negligible, right? And because even though it's 1 times 10 to the negative 7th, because this is all dissolved in water. But anyway, so then these guys, you look at this, and so the HClO will react to create the hydronium. So its concentration will go down by X, and then the guys on the other side of the equilibrium will go up by X. And so then the equilibrium concentration will be 0.1025 minus X, and of course ClO 0.1042 plus X, and then the H3O plus X. Now think about this. The important number here that we're going to have to solve for, because the initial question said what is going to be the resulting pH if you mix those solutions together, the HClO and the KOH, right? Well, once you mix them together and all the KOH is used up, right, you still have some HClO minus. So that HClO minus is going to then act, like what it does, right? And so you end up then wanting to calculate what the resulting pH would be. Okay, so what you know is then you say, well, these X's are going to be small, right, in relation to... All right, guys, so actually I stopped the recording there because I realized as I was looking at this, something didn't make sense, right, because I was talking it out, and I realized I sort of have a mistake kind of in the notes. No biggie, I caught it. It's when I was saying that X is going to be small, right? So this X is going to be small in relation to the 0.1042. So when I wrote my Ka down here, I realized that's my mistake, right? It should be what this should actually read down here is this product concentration times X. So hold the presses here. I'm gonna fix this. This should be 0.1042 X times X. And that's over this concentration on this side. Again, assuming X is small, you can just put in 0.1042, and then the times X is for the hydronium's X, okay? You're assuming this, again, is very small. So sorry about that. At least I caught it. Anyway, the math down here was correct. The only thing wrong was the fact that I had X times X instead of 0.1042 times X. So when you solve, though, for X, you do get X equals 3.48 times 10 to the negative 9, all right? And that's the hydronium ion concentration. And so then you have the pH is the negative log of 3.48 times 10 to the negative 9th, and you get a pH of 8.495. Now you may ask yourself at this point, okay, well, Mr. S, we had this HClO and it's reacting with water. That's an acid reacting with water. Why didn't it end up with an acidic pH? Well, now we can kind of look at the concentrations. Well, at equilibrium, right, if you look at this, kind of the way it's set up, you have much more conjugate base present than you do the acid. And so what ends up happening is in this equilibrium, the pH ends up being, that conjugate base, you have a greater concentration of the conjugate base with its acid, and so it ends up at a basic pH. So that is not, it's kind of maybe surprising, but not once you look at the concentrations that were present. Okay, third scenario. Weak acid versus strong base, but it's one where in the wording of the problem you realize that there's no dilution. So you're thinking there is a reaction though between an acid and a base, so there's going to be stoichiometry. You are thinking and because there is a weak acid involved, or or if it's a weak base or a strong acid, there might be an equilibrium. But we are going to see in this case, is there an equilibrium? The answer is no. And that's because after we do our stoichiometry, we are going to find that in this scenario, we will be at the equivalence point after stoichiometry. So anyway, let's look at the way this question is worded. What would be the pH for a 100 milliliter, 100 milliliters of the following solution containing final molarities given? Okay, and so you have 0.2500 molar HClO and 0.250 molar NaOH. Okay, you can kind of tell. So that's what would the pH be? Okay, well, you know that you're going to be at the equivalence point, and so because the moles of acid equals the moles of base. Okay, but we'll see this when we do the stoichiometry. But is there a dilution? Well, you can kind of tell no, because it says these are the final molarities. Okay, so you have a 100 milliliter solution, and this are the final molarities in there. So you've already been given the molarity after the two solutions have been added together. Okay, so stoichiometry, yes. And actually, I misspoke myself. There will be an equilibrium at the end. That was incorrect. I was thinking strong versus strong. Anyway, let's just look at the stoichiometry, and then we'll see why there is an equilibrium at the end. So I set up my reaction, HClO plus NaOH. It's going to make the salt, sodium hypochlorite, and water. Okay, let's write the net ionic equation. Well, sodium is the spectator. So let's write our before. Again, we didn't have to do any dilution calculations because those were the concentrations. Well, they're going to react in a 1-to-1 mole ratio, and so and they're equal to one another. So this one's going to go down by 0.2500. This is going to go down by 0.250, right, times 1/1 mole ratio. And so what you end up with is, after the reaction, there is no HClO remaining, no NaOH, well, no OH minus remaining, at least from this reaction. But what's going to happen to the ClO? Well, all of this HClO is going to be converted into ClO minus, right? All of this. And so that concentration, when this conversion happens here, is going to be, will make 0.250 molar hypochlorite ion. So after the reaction, you have some conjugate base, and it's going to be present in water. Because you are at equivalence, okay, ClO minus is the only species present. This will represent, thinking back to the titration of weak acid versus strong base, this is going to be the point in the titration, right? Here's your pH. This is the amount of NaOH added. It's going to be like this. Here's the, right? We're going, do like that, right? And this was pH 7, right? Remember how we said that at the equivalence point, this is pH 7, at the equivalence point, when you have a weak acid versus strong base, the pH at the equivalence point ends up being greater than 7 because you have conjugate base present, and there's no HClO and no OH minus present at that point because they've neutralized one another. And now we're going to see when we do our equilibrium, yes, because now we have an aqueous equilibrium of ClO minus in water, and now we want to see, well, how much, what will that guy do? That guy is going to produce some hydroxide, right? And that's why we're going to end up in equilibrium with water, and so you're going to end up with a pH above 7. Let's look at the ice table for this one. So you have to write the reaction. It's going to be that conjugate acid, that conjugate base plus water. So essentially what you're doing is you're taking this product side and you're saying, well, there's no more of this present over here, this stuff over here present. So now it's just a basically pure water, pure ClO minus and water. But what that's going to do is react, and it's going to, well, how will that look? Well, here's your Bronsted-Lowry reaction. You'll make OH minus and HClO. Okay, so at the beginning, what do you have? So let's do our ice table. The initial concentration of ClO is there, and these guys are 0, right? Because the reaction is just now going to start. Once all of the HClO was used up and the OH was used up, you have this conjugate base in water. Well, you know the equilibrium is going to go in this direction because you have no product. So this is going to go down by x. These are going to go up by x. So at equilibrium, here we go with that same approximation. This is going to be 0.250 minus x, and these guys are going to be x. Okay. Now, you got to remember what is present. This is the conjugate base of ClO minus. And so you know when you write your equilibrium expression to calculate the concentrations of X, okay, you don't have any HClO present. It's only ClO minus. So when you write the KEQ, right, where you write that the KEQ is going to be equal to X times X over 0.250. Well, that's not going to be the Ka that's given up here, right? That's if you had HClO present left over, right? But you have, I'm going to move the recording window up a little. Okay, you have only ClO minus, and so what this is going to be equal to the Kb. So remember, how do you find Kb? Well, Kb times Ka equals 1 times 10 to the negative 14th. That's one of the equations they give you, just like we know that pKb plus pKa equals 14. So you first solve for the Kb. Again, it's Kb because all that's present is a conjugate base. So the equilibrium is going to be based on the equilibrium constant of ClO minus, which is the Kb because it's a base. Anyway, so you do this, and that equals 3.4 times 10 to the negative 7th. And then that's going to equal this concentration times that concentration divided by this concentration where you assume X is small. In the end, what matters now is what's really going to matter is the concentration of OH minus, right? So you end up, if you solve this equation here, with X equal to 2.9 times 10 to the negative 4th. That's the concentration of OH. Well, again, the question asks you, what is the pH of this resulting mixture? So when you take the negative log of this number here, 2.9 E minus 4, you're going to get the pOH. So the pOH would be 3.53. Then the pH of this remaining solution, again, this is the solution that remains after these two guys react, right? You were at the equivalence point, but the ClO minus now is left over, and so at the end of that, you end up with a basic pH, right? Because you end up having this second equilibrium creates some OH minus, and then so that the pOH would be 3.53. And the pH is 10.47. So again, if you, in this kind of scrolling back up to kind of look at this titration, right, then this point here, right, that's pH, the pH where you have your equivalence point, right? What would the pH be? Well, the pH at the equivalence point where you add an equal amount of acid here and equal amount of base, right? You're at the equivalence point. This pH would be that pH 10.47. Okay, last scenario. Weak base versus strong acid. And you're going to see that it's going to end up where you are at that half equivalence point after the stoichiometry step. And then we're going to kind of see what that means, okay? Or how that looks on the titration curve. What would be the pH if 30 milliliters of 0.2 molar NH2OH is combined with 15 milliliters of 0.20 molar HCl? And in that wording, you can tell dilution, yes. You know there's a dilution, okay? So you have to figure out the new concentrations. And so the concentration of N2OH is 0.1333 molar, and the HCl will be 0.06667 molar, all right? let's write the reaction. Well, again, in the net ionic equation here, right, this in the net ionic equation, the Cl of the HCl is a spectator. So you could write HCl, but you know the net ionic equation is going to be H+. Okay, so you have an acid, you have this base. The base is going to accept the hydrogen, okay, and make NH3O with a plus, right, and then H2O. Okay, there's your neutralization reaction. You're creating water. Looking at this initial, this is so is there stoichiometry? Yeah, because you're reacting these two things, right? And we want to know what the pH is, and so we need to find out what we have left over after the stoichiometry occurs. Before, these are your two concentrations. If you kind of look at this, then what's going to happen is, well, there's not enough H+. It's the limiting reactant. You don't have 0.1333 molar H+. You have 0.06667 molar. And so this is going to be the limiting reactant. It's going to go down, and its final concentration is going to be 0. But if you kind of look at it, if you look at these numbers, I have a little green star there. You can see that you have a certain amount of base, but you've added half of the molarity-wise of the base. And so this is what we would call that half equivalence point. I mean, we're halfway. If we had added, in this case, at this point, if we had 0.1333 molar HCl, right, after the dilution, then we would be at the equivalence point. But we're not. We've only added half as much to get to the equivalence, to an equivalence. Moles of acid equals moles of base. Stoichiometric moles of acid equals stoichiometric moles of base, right? So you kind of see this is going to be the half equivalence point. So this goes down to 0. This is going to go down by the 0.0667 times the 1-to-1 mole ratio. So that's what it's going to go down. And you see that you've neutralized half of the NH2OH, right? But you've created that same molarity of its conjugate acid. Remember, this is going to be a conjugate acid of NH2O. And even though we'll get to this in a second, but why? Because this guy could do this and create hydronium. So at this point, you realize you're at the half equivalence point because the concentration of this base and its conjugate acid are equal. Okay, so now these guys are going to set up an equilibrium because they're going to be present, right? They're going to be present in water. Okay, and so you write the equilibrium. So just like we did before with the one where we ended up with an equilibrium, we write the reaction, right? But it's going to be, this guy is going to be present now. This guy is going to be present, and you write it as present in water. And then you're going to create your ice table. So NH2H plus water, right? How would the reaction go if this guy were dissolved in water? Well, the water is going to act as the acid. This is going to act as the base. You make NH3O plus, and you would get OH minus out of it, though, right? Okay, that's how it acts like a base. It ends up reacting, right, with being a proton acceptor, and then creating some hydroxide. At your initial concentration, thinking of, okay, yeah, I'm here. I'm at this point right here, and now the reaction is going to start with the water that's present in the solution. My initial concentration here is 0.0067, and here it's 0.0067. It's what you get. It's the concentrations at the end of the stoichiometry. All right? Again, you're going to write it. This is going to create the base, so this is going to go down by x, and these are going to go up by x. Again, you assume both of these x's are small, right, in relation to the concentrations present. Okay, it's the assumption you have to make, otherwise you have to use a quadratic equation solver. Now, NH2OH is a base, and you were given the Kb at the top, right? 9.1 times 10 to the negative 9. So you were given the Kb, and this is the reaction for a base. So you can use the Kb directly. In other words, you don't have to use Ka for the NH3OH plus. So you set up your KB. It's going to be this times this over this. And what you find out is, oh, X, the concentration, right, is equal, because these guys then cancel, it's the half equivalence point. The concentration of the reactant, the base, is equal to the concentration of its conjugate acid, right? And so, and the concentration of OH ends up being the KB, and then the POH ends up being the PKB, right? So it's kind of neat, right? Remember that's at this point here, right? Right. And so yeah, so then you have so anyway, so that's the POH, right? Because this is the OH concentration, X is the OH concentration. Take the negative log, you get this, and then what would the pH be? Okay. So then again, so this half equivalence point is an important point for weak acids versus strong base. The half equivalence point, the POH, the pH equals the pKa. For weak base versus strong acid at the half equivalence point, the POH equals the pKb, and the pH, this pH here, would be the pKa for the conjugate acid, in this case, the NH3OH. Okay, so remember, this pH here wouldn't be the pKb for NH2OH. It's going to be the pKa for the conjugate acid. Okay, but the pKb will be the POH for the base. Okay, I hope this isn't too confusing. I think at this point you just need to go through some practice problems. Again, ask yourself the 3 questions. Is there a dilution? Is there a stoichiometry? Be very meticulous at writing that stoichiometry out. Once you get to the after in your stoichiometry, you look and see what's present, right? If there is any weak acid or its conjugate or its conjugate present, then a weak, they set up an equilibrium. You'll do an ice table, and you'll either find at the equilibrium concentration, depending on what you're reacting, it's either going to be H3O or OH minus. Take the negative log of that, get the POH and or the pH. So just kind of follow along. Also, for this guy, with the worksheet, I've posted the key to Canvas. So if you get stuck, when you're doing the worksheet, just kind of eyeball the key, not to just copy it, right? But maybe to see, like, I'm not sure what to do here. Is there an equilibrium? Is there not an equilibrium? You can check the key. And then, if they're yes in equilibrium, don't just copy the answer. Go ahead and work it out just to see. So the key is posted, so you can do some troubleshooting if you're having trouble. All right.